In this section, we are going to be graphing polar equations. Just like with a rectangular coordinate system, a solution is something that makes the equation true. So whenever you have, let's say, a linear equation and you have a coordinate of xy that makes the equation statement true, that's a solution. Same thing is going to be true when we use the polar equation ordered pair with r and theta. And the graph of the polar equation is a graph of all of the solutions to that equation. So just like with the rectangular coordinate system, if you had a line, all of the points on that line would make that equation true. Same thing for a graph of a polar equation where it is all of the ordered pairs that make that equation true. You understand typically what a function looks like based on what the parent function is. Let's say you have something that is y equals x, you know that that's going to be some sort of linear graph. If you have y equals x squared, that's going to be a parabola that is U-shaped. If you have y equals x cubed, that's going to look like an S that's sideways. You understand what an absolute value function might look like, or an exponential function, but when it comes to polar equations, you might not know what the parent function looks like. Just like when we started out graphing linear equations, we're going to graph polar equations by plotting points. And so what you do is you pick some points and plug in those values to determine what the r value is. So you're going to be picking theta, plugging theta into the equation, and then solving for r so that you get an ordered pair, r theta, that you can plot on the polar coordinate system. What you see here on the right-hand side, this graph that has a circle, it's the equation x squared plus y squared equals 4, which we recognize as a circle centered at the origin with a radius of 2. This is equivalent to the equation r equals 2. That means that for every theta, you're going to have an r value of 2, and so that's why the circle comes in. If you're going to be plotting points, again, remember you're going to be picking theta, substituting theta into the equation, and finding the matching r value. To graph a polar equation by plotting points, choose values for theta, substitute those values into the given polar equation, solve for r, and then plot the ordered pair r theta on the polar plane, and then you connect those points. Essentially, you are creating a table of values just like you would in the rectangular coordinate system. There are three equations that represent circles in polar coordinates. Whenever you have r equals some number, the radius is the absolute value of that number, and the graph is centered at the pole, so it's centered at the origin. If you have r equals a sine theta, the diameter, not the radius, is the absolute value of a, and it's centered at theta equals pi over 2. Now, if a is negative, then the circle is below the polar axis. So to the right, I've drawn a very rough sketch where you've got the yellow circle above the polar axis, and if a is negative, the red circle is below the polar axis. If you have r equals a cosine theta, the diameter again is the absolute value of a, and it's centered at the polar axis. And if a is less than 0, the circle is to the left of the pole. So yellow is if a is positive, red is if a is negative. And notice that we're talking about the pole, or theta equals pi over 2, or the polar axis. We can use symmetry to help us graph equations using polar coordinates. And we have symmetry with respect to the pole, to the line theta equals pi over 2, or to the polar axis. You have symmetry with respect to the polar axis if you get the original equation by plugging in negative theta. Remember, using rectangular coordinates, if we had f of negative x and we got f of x, if we plugged in the opposite of x and we got the original function back, that was even. If we plugged in the opposite of x into the equation and we got back the negative function, that was odd. So when you're testing for symmetry, you are replacing by the second thing. So we're talking about r negative theta. So you're plugging in negative theta, and if you get the original equation when you plug in negative theta, then you have symmetry with respect to the polar axis. Same thing about the line theta equals pi over 2. If you substitute in pi minus theta in place of theta and you get back the original equation, then you have symmetry with respect to the line theta equals pi over 2. And lastly, if you substitute in a negative r and you get back the original equation, then you have symmetry with respect to the pole. This graph to the right shows you the different parts that we're talking about. The polar axis is what would be the positive x-axis. The line theta equals pi over 2 is what would be the y-axis. And the pole is the origin. So when we're talking about symmetry, you're talking about either to that polar axis, the line theta equals pi over 2, or the pole. If you substitute in one of these values, depending on what you're testing for, when you're testing, you have to test all three because there are three different things that you're substituting in. So when you test and you substitute in and you don't get an equivalent equation, then you have what's called inconclusive evidence. So if the test for symmetry fails, the graph still might have that symmetry. So just because you plug in negative theta and don't get back the original equation doesn't mean it's not symmetric with respect to the polar axis. It just means that it's inconclusive. Because remember, there's an infinite number of points that represent these different polar coordinates we're talking about. Another thing that you can use when you're graphing polar equations is to figure out what the maximum value of the absolute value of r is if it exists, because this gives you the distance from the pole to the point or points on the graph that are farthest from the pole. And this can be helpful in graphing by hand when you're setting up your graph or when you want to use a viewing window that's appropriate on a graphing utility. So identifying that maximum value of the absolute value of r helps you create an appropriate graphing window when you're using either a graphing utility or if you are creating your graph by hand.